When two atoms are bonding, they are going to bond using their valence electrons. The core electrons are in the middle of the atom, and they do not participate in bonding, and they are in complete energy levels. Bonding occurs when valence electrons try to stabilize the outer energy level, and they are the ones that participate in bonding. And remember, if you are in group 1, you've got one valence electron. If you are in group 2, you've got two valence electrons, 3 in group 3, 4 in group 4, 5 in group 6, 7 in group 6 in group 6, 7 in group 7, and none or 8 in group 8. Remember that from here onwards, it could be 13, 14, 15, 16, 17 on the periodic table, but you don't worry about the little ones. They not really what we're interested in. We're looking at the number of valence electrons. Okay, and if you're taking a look at your periodic table over here, this is the one that you'd be given. You're in group 1, 2, 3, 4, 5, 6, 7, and 8. And they have that number of valence electrons. This is just an animation which I showed you last year of the valence electrons. So you've got the core electrons all the way in the middle over there, and just 2 in the outer energy level over there. And this is the same sort of story over here, where they can all move around, and there will be 2 valence electrons. The number of electrons that participate in bonding tells you what is called the valency of the atom. And that is like your bonding arm. So generally, group 1 has 1, 2, 2, 3, 3, 4, 4. And then from 5, it's 8 minus 5, 3, 9, 8 minus 6, 2, 8 minus 7, 1, and 8 minus 8 is 0. The transition elements, except for zinc and silver, have got variable valencies, and we need to use stock notation to tell us about them. Sometimes group 4 to 6 will vary their valencies, and we use stock notation to override the default. So what is the valency of the underlined element? Sodium is in group 1, so its valency will be 1. Calcium, chloride, chlorine is in group 7. 8 minus 7 is equal to 1. Iron 3 bromide, that tells me the valency of the element in front of it, 3. Sulfur 4 oxide, oxygen is in group 6. 8 minus 6, valency 2. And writing the chemical formulae of each of these, just a reminder, sodium is Na with a valency of 1. Hydroxide is polyatomic. You now need to learn your polyatomics. And so it's NaOH. Calcium chloride. Calcium has a valency of 2. Chlorine has a valency of 1, so it's CaCl2. Iron has a valency of 3. Bromine has a valency of 1, so it's FeBr3. And sulfur 4 oxide, the sulfur has a valency of 4, whilst the oxygen has a valency of 2, so it turns out to be SO2. We've done a lot of this last year. You should be fine with it. Draw Aufbau diagrams for the following. If I take a look at phosphorus, I'm going to say, just draw my little box for Aufbaus. They're a bit of a pain to draw, really. 1s, 2s, 2p, 3s, 3p. And phosphorus has got 15 electrons in the outer energy level, so it's 1, 2, 3, 4, 5, 6, 7, sorry, there's a line there, 8, 9, 10, 11, 12, 13, 14, 15. Calcium 2 plus means that it has lost 2 electrons, so where calcium would have had 20, there are only 18 electrons you insert, and chloride means it is the ion, which would have been 17 plus 1 extra electron is also 18. When I have to draw electron configurations, for example, if I'm going to do sulfur, it's 1s2, 2s2, 2p, 6, 3s2, 3p, 4. That is the 16 electrons represented. Oxide means that I need to add 2 extra electrons to what oxygen normally has. 8 plus 2 is equal to 10 electrons over there. And finally, potassium would normally have 19, but it's lost 1, so it's going to be 18 electrons that you represent using the electron configuration. Those are all represented in the slide over here. If necessary, press pause and double check your answers. Unpaired electrons participate in bonding, so now, unless they're going to hybridize, remember carbon has a tendency to hybridize where they open up like that and have 4 bonds instead of 2, but generally speaking, you can only use unpaired electrons. So, for example, 1 with fluorine, there's 2 unpaired in oxygen, 3 unpaired in nitrogen. And here we have a whole lot of Lewis dot diagrams. Remind yourself, oxygen has got 6 valence electrons. If I've got 2 shared pairs, my Cooper notation has 2 arms in between. Oxygen shares 1 electron with hydrogen, and I draw that with 1 line between them. Nitrogen has 5 valence electrons. It bonds to 3 hydrogens with its 3 lone electrons, and they pair up, and your hydrogens join on, and I get NH3. Nitrogen shares 3 electrons with another nitrogen, and again, this is recapping last year. It shouldn't be a big surprise. Remember, oxygen and hydrogen were nonmetals, sharing. Nitrogen and hydrogen, nonmetals, sharing. Oxygen and oxygen, nonmetals, sharing. Nitrogen and nitrogen is sharing again, 2 nonmetals. The minute I've got a metal like sodium and a nonmetal like oxygen, the electrons are going to transfer, and I'll end up with an ionic bond forming. I need to write the positive ion and the negative ion with its extra electrons. Again, lithium oxide, the lithium is a metal, oxygen is a non-metal. Electrons go from lithium to oxygen. Magnesium metal, fluorine non-metal. Electrons go from magnesium to fluorine. Carbon is a non-metal, oxygen is a non-metal. So they're sharing electrons, and I can represent that using Cooper notation. I can't use Cooper notation for ionic bonds. So I'm going to look at carbon tetrachloride over here. Notice it becomes this sort of symmetrical molecule with polar bonds, but it's a non-polar molecule. And I'll end up with sharing 1 pair, sharing 1 pair, sharing 1 pair, sharing 1 pair, and I can represent that with Cooper like that. So if I carry on looking at these diagrams, hydrogen shares 1 pair, 2 nonmetals, so it's a covalent bond, and because of the equal electronegativity, it is a non-polar covalent bond. Chlorine and chlorine have the same electronegativity, 2 nonmetals, non-polar covalent. Hydrogen and chlorine have got different electronegativities, so it's hydrogen and chlorine, polar bond. So nitrogen and hydrogen, 2 nonmetals, but they're uneven electronegativity, so I get a polar bond. Oxygen and hydrogen, uneven electronegativities, a polar covalent bond, they're both nonmetals. Oxygen and oxygen, again, it is a non-polar molecule and a non-polar bond. Nitrogen, also a non-polar, nitrogen and nitrogen have the same electronegativity. When I look at carbon and hydrogen, it's got an electronegativity of 2.5 for the carbon and 2.1 for the hydrogen. When I bond those, I find that they have an electronegativity of only 0.4. It's a minimal electronegativity difference. But also this molecule is completely symmetrical. The polarity to the top equals polarity to the bottom. Polarity to the right equals polarity to the left. So any pull that might have happened in any direction is balanced out, and the molecule as a whole is a non-polar molecule. Calcium is a metal, transfers its electrons to fluorine, which is a non-metal. Ionic bond. Ionic by its very nature is polar. Sodium transfers metal to non-metal, oxygen. Magnesium, metal to non-metal, sulfur. All of those are transfers of electrons and ionic. Again, going through all of these, we're going to do Lewis dot. Fluorine, it's identical atom, so it's a non-polar molecule. Lithium is a metal, chlorine is a non-metal, transfer the electron. Magnesium is a metal, iodine is a non-metal, transfer the electron. Ionic, ionic. Sulfur and hydrogen, there is an electronegativity difference, you get a polar molecule. Phosphorus and hydrogen, you'll notice, by the way, sulfur is in the same group as oxygen. This looks a lot like water. Phosphorus is in the same group as nitrogen. This looks a lot like ammonia or NH3. Both are polar molecules. Potassium, metal, transfers its electron to sulfur. Carbon tetrachloride here Looks a lot like that methane or that CH4. Again, what the polarity up equals polarity down, polarity right equals polarity left, and so overall it is a non-polar molecule. We call this shape tetrahedral. Hydrogen and fluorine, electronegativity difference is 1.9. It's one of the highest electronegativity differences. In fact, one might even think it was ionic. But because it's two nonmetals, we tend to think of it as very polar covalent. Calcium and sulfur, metal to nonmetal, ionic transfer. Carbons, at least hydrogen cyanide, is carbon bonded to hydrogen and to nitrogen. Triple bond to the nitrogen. So I'd have triple bond to the nitrogen, single bond to the hydrogen, and that is also a polar molecule.